Hi, good afternoon, everyone. I'm Wikke from the Antwerp Maritime Academy and soon also from the University of Ghent. I'll be presenting my work on the SOCORRO project, seeking out corrosion before it's too late. A short introduction to SOCORRO. Corrosion is a project on the corrosion of commonly used construction steels in a maritime and industrial environment. A couple of short facts about the existence of this project. The cost of corrosion can be very high, up to 3% of the GDP, or in a maritime related context, for example, 30% of port costs. There are a lot of different parameters influencing uniform corrosion. Uniform corrosion is the topic of the SOCORRO project. It can be influenced by temperature, salinity, pH, conductivity, and more parameters. The interaction between these parameters themselves can also can complicate the prediction of corrosion in assets, in steel assets. Furthermore, measuring corrosion is difficult and is often done only after the fact. For example, visual inspections, ultrasound inspections, and in a maritime context, diving teams are necessary to do inspections on corrosion. And of course, this only takes place after corrosion has happened. The aim of the project is to create a data set with water quality parameters, in this case pH, temperature, salinity, oxygen, and conductivity, and also create a data set on corrosion rates. The aim of the project is to create an artificial intelligence algorithm where you can input water quality parameters, and then the algorithm will calculate risk of corrosion for you. The artificial intelligence algorithm is trained on 3 different alloys, S235, S316L, and S355. So commonly used construction steel in this maritime and industrial environment. The outcome of the artificial intelligence algorithm will be a red, yellow, or green situation for the alloy you're using in a set of water quality parameters. My work is on the experimental setup where we generate initial training data and where we do sensor testing, and afterwards we are now in the process of going to field demonstrations for more extensive training data and to demonstrate this technology in a real-life case. All of the data will be used to train the artificial neural network and then calculate risk of corrosion. And to counteract the black box syndrome, which often comes with algorithms, an analysis of the relationships between the parameters and corrosion is performed, and literature data comparison is also done. Today I will be talking more about my setup, which is a setup at the Antwerp Maritime Academy, where I have a glass basin in which I have different corrosion sensors and water quality parameter sensors. I can measure temperature, dissolved oxygen or P, conductivity, pH, chloride, and chlorophyll. I can modify the solution and then record all of the data. In the setup, I use a diluted ASTM seawater to generate brackish water, and right now we're using argon to displace oxygen. The design of the experiment was to 2 times per week change the parameters inside of the basin. So salinity and therefore conductivity was changed. In brackish water conditions, the temperature was varied, dissolved oxygen, and the pH. Half-hourly, the instantaneous corrosion rate was measured on S235 carbon, low alloyed carbon steel, and the imbalance was also measured. All of that was done by linear polarization resistance measurement, and this is an industrial system, so it can also be used in the demonstrators. Then the water quality parameters were measured, and some reference measurements were also made to check the industrial instruments, a linear polarization resistance measurement with a potentiostat, and weight loss measurements on corrosion coupons, which were also suspended in the solution. Over here, I will quickly show you the time series, which is not that interesting when you look at it for over 120 days worth of data. But during the experiment, I used this extensively. On the left-hand side, from top to bottom and left to right, you can see the temperature, the dissolved oxygen, the conductivity, the pH, the redox potential. The salinity is also displayed over here because it's nice to see it's highly related to the conductivity, but it filters out the temperature influences on the conductivity. And on the left-hand bottom corner, you can see the measured corrosion rate in millimeters per year, which varied around 0.3 to 1.6 millimeters per year. On the right-hand bottom side, you can see the imbalance. On this data set, principal component analysis was performed. Principal component analysis basically reduces the dimensionality of the data set, and it allows you to observe a relationship between parameters very easily. The original coordinates of the data set are converted to coordinates on principal component axes, and as the left-hand side, there are only 3 components necessary to display over 90% of all of the explained variance within this data set. So on the right-hand side, you can see the plotted data on principal component 1 and 2, and I'll go through the data with you. The corrosion rate is color-coded in this data set, and the measured parameters are shown as vectors in this graph. This shows that the temperature and conductivity are highly correlated, and they are negatively correlated with the dissolved oxygen. And you can see that the ORP and pH in this graph are negatively correlated as well, but do not have a big correlation with the other environmental parameters. As you can see, the color gradient, it goes from black to very yellow. This is around 0.3 millimeters per year to 1.6 millimeters per year. And it shows that the corrosion rate is highly correlated with temperature, conductivity, and negatively correlated with the dissolved oxygen in this data set. Around 74% of explained variance is displayed in this graph. Then there are the 2 other graphs with principal component 1 and 3 and 2 and 3. The left-hand graph shows that the temperature and conductivity are still correlated and also correlated with the ORP, but to a lesser extent because the vector is a little bit smaller. And they are together negatively correlated with the dissolved oxygen. Also, the corrosion rate data still follows the principal component 1 axis, and you can see that there's a color gradient from black to a very low corrosion rate to a very high corrosion rate. On the right-hand side, there's principal component 2 and 3, and the corrosion rate is not very well displayed on this graph, as is the conductivity, temperature, and the dissolved oxygen. They constitute less variance for these parameters is displayed in this graph. However, pH and ORP are represented in this graph, and they show no correlation whatsoever for these 2 principal components. As a small conclusion from this principal component analysis, we can conclude that corrosion in brackish water is correlated with conductivity and salinity and the temperature. It is, however, not correlated with the redox potential and the pH in this data set. Some reference measurements were made with the linear polarization resistance method with the potentiostat, and this shows actually a comparative measurements. However, there was a discrepancy between the coupon weight loss method and the linear polarization resistance method. The coupons showed over the course of 1 month only a corrosion rate of 0.24 millimeters per year, and the LPR system a corrosion rate, an instantaneous corrosion rate between 0.6 and 1.1 millimeters per year. Some difficulties encountered in this experiment was the removal of the dissolved oxygen. I used sodium hydroxide for that, but it does influence the pH, and it's quite difficult, as you can see in the previous graphs, to keep it at a low dissolved oxygen level for over longer periods, because it reacts very quickly, and overnight all of the dissolved oxygen would re-enter the basin, and your sodium hydroxide would be consumed. Then there's the weight loss discrepancy, as I mentioned before, and the imbalance measurement is actually a qualitative measurement, and it's quite difficult to quantify it because the imbalance in a 2-electrode system between 2 electrodes only gives you an indication of pitting tendency. So when this measurement would be higher than your uniform corrosion rate measurement, this would indicate that you have pitting tendency instead of uniform corrosion. This was not the case throughout the experiments, and I was not able to quantify it on the electrodes of the measurement system. Then there was a small difficulty in the pre-processing of the data. So the aim of the project is to feed all of the data to an AI algorithm, and it has to be done automatically. So I performed a couple of small experiments in the same solution, and I would suspend the LPR system within the solution for a couple of days, take it back out and clean it, and then re-enter it into the same solution. And as you can see, for this solution, you measure different corrosion rates, which is especially true for the first day. You can see that there's a stabilization needed for the corrosion rate, as is usual in corrosion measurements, that you would let the open circuit potential stabilize over the course of a few hours. So what I've done is try and come up with a solution for this problem, because within one scenario, within one set of given water quality parameters, you would measure different corrosion rates. And this would not be valid, this would not be wanted for the AI algorithm. So I use the Savitsky-Golay signal processing filter to smooth the measured corrosion rate, and this would allow me to take the first derivative of the smoothed data. Based on the small experiments that you saw in the previous slide, an allowed change of 0.06 millimeters per year per day was chosen in order to filter out every data point where the first derivative would be higher than that. So an example of this pre-processing filter is shown over here, where you have the blue line, and in this point, right before day 36, the environment would be changed, and then you would see the corrosion rate increase dramatically and then stabilize over the course of a few days. The purple line is the smoothed signal from the Savitsky-Golay filter, and the green line is the accepted corrosion rate data by the pre-processing filter.
Are you close to wrapping up, Wikke?
Yeah, very close. The next up on the is the lab experiment, which will be further performed for seawater. I will change the scenarios a little bit according to the pre-processing filter. And right now, demonstrations at the Antwerp facility of BASF and at the port of Ostend are being set up. Thank you for your attention.